So when you have an IR and you have a particular peak you're looking at, like that spectrum we just saw, there were peaks at around 3,000. They had all those little peaks in the fingerprint region. What's responsible for each one of those? Three things. I already mentioned this, the strength of the bond, right? Some bonds are simply stronger than others. Okay? Carbon-oxygen double bond is stronger than a carbon-oxygen single bond. And that's why it appears at about 1,700, while the CO single bond appears at about 1,000. Okay? So strength of the bond matters. Also, masses of the atoms involved matter. You don't see that much in a way that you can really look at it qualitatively and say something about it. One place, though, for comparison purposes is to think about a CH bond relative to a CD bond, right? Deuterium instead of hydrogen. You can also sort of ask that question with CO versus CN. Not a big difference there, though. Big difference between carbon hydrogen and a carbon deuterium. Oh, and in the parentheses, of course, are the sum of what the difference is. Stronger bonds, higher frequencies. Lighter masses occur at higher frequencies, right? The heavier weight vibrates a little more slowly when it's on the same bond. And the type of vibration being observed. There are two types of vibrations to keep track of. Stretching and bending. That's it. That's pretty easy. And again, just think about the analogy of the spring. What can you do with the spring? You can stretch them, you can bend them. That's it. And also that summation there, the stretching vibrations occur at higher frequencies. So roughly the middle of the IR spectrum is very rough. And to the left of that are all stretching, and to the right are primarily bending. The point to this exercise was really to get you to think about stretching and bending in the context of a molecule, right? You can think about an isolated spring, and that's not hard, because a spring can do this. But what happens when a molecule has more than just two atoms? Right? Now you got the problem of three. So they can both be going in and out at the same time, right? Or opposite each other, right? My joints pop and snap too much these days. I don't want to do that. I want to get recorded. What's all that noise? Sounds like they're making popcorn. Right? And that's something to think about. And what happens now when you add another atom? And suddenly you've got a bunch going back and forth at the same time. Or not. Right? I can't chew gum either. And walk at the same time. Man, you ever bite your cheeks? All right. But anyway, so this is the thing, this is the next level to think about with IR. So within the context of stretching, and you have more than just two atoms, you have to think about, are the stretches occurring in a symmetric pattern? They're both going in and they're both going out at the same time, or is one coming in while the other's going out? And that's asymmetric stretching. Both occur in, when you're looking at a sample of a molecule, it's all happening, right? Because you got more than one molecule. And then likewise with bending. When you think about bending, right, two hydrogen atoms, I'll play the part of the carbon. But two hydrogen atoms are going to be doing this relative to each other. Right? That's kind of a symmetric bend. We call that scissoring in the context of IR spectroscopy because it's doing what scissors do, right? Also, they can do this. Okay? So there's a lot of motion that can be going on. That's a bending where they're both doing the same thing at the same time, right? They're both going to the left or to the right, from my perspective. There's another type of bending that can happen. That's in the context of a plane. They'll go up and down through the plane. All right? So there are a couple of different things that can happen. Because this is also that same idea. Thinking about the whole sample of the molecule, not just, the whole sample of a compound, not just a molecule. First point is the first point is concentration matters. Well, does that make sense? If you have a very concentrated sample, then you have a lot more, let's say, carbon-hydrogen bonds for the IR energy to interact with, right? So peak intensity is related to the concentration of a sample. If you got too much there, maybe none of the IR is going to get through. That's a problem. You can dilute the sample then and retake the IR, and maybe you'll get a good spectrum. Okay? Makes sense. Relative peak intensity is also additive. The carbon-hydrogen bond, we'll talk about why next time, but the carbon-hydrogen bond is not a strong absorber of infrared energy. But the peak representing carbon and hydrogen bonds is usually very strong. Why? Because you got a lot of them. Even lowly methane has 4 carbon-hydrogen bonds. And they all add up as far as the infrared absorption goes. Okay? Here's the third point, and why carbon and hydrogen is not a strong absorber of infrared energy. The intensity is due to the dipole moments. Stronger dipole moments absorb infrared energy better than weak dipole moments. So you think about carbon and hydrogen, that dipole is not very intense. That's why the carbon-hydrogen bond is not a good absorber of infrared energy, but you always have a lot of them, so the additive effect is there. Typically, you'd only have 1 carbon-oxygen bond in a molecule, like an alcohol. That dipole is quite strong. And why then the CO bond, even though there's only 1, always gives a strong absorbance.